Next talk is given by Veneranda López Días on the theoretical model for isotope fractionation during water ice sublimation under lunar environments.
Yeah, so hi everyone, I'm Veneranda from LIST, and I will talk about a theoretical model for isotope fractionation during water ice sublimation under lunar environment for a more robust interpretation of water ice isotope signature from future lunar missions. As you already know, water is a key resource for the establishment of sustainable robotic and human presence on the moon. And the lunar water isotope signature will give information about its origin and distribution and redistribution mechanism. So this will help to answer some scientific open questions like origin of water in the Earth-Moon system, distribution and redistribution mechanism, Earth-Moon system history, and water futures on Earth and in space. Regarding space mining, it will help to determine whether these water deposits can be considered as resources or reserves, and also to help to design the extraction, detection, processing, and beneficiation technologies. And so there are several lunar missions planned for ice prospection on the moon, targeting analysis of the surface and exosphere. And for a more robust interpretation of the raw data coming from those missions, we need to understand the extent and nature of any potential water ice loss and related isotope fractionation during the sampling chain. And for a current interpretation of the lunar water cycle, we need to understand how this isotope signature is modified along the lunar water cycle. The sublimation rate in ice, the sublimation rate of water ice in low pressure system at very low temperatures and related isotope fractionation are poorly understood. There are a few equilibrium fractionation factor models done fitting data from deposition experiments that were done only down to 233 kelvins. And when we extrapolate those models down to very low temperatures, it returns in non-coherent data, as you can see here in the dashed and dot lines. And there is the limited data on isotope fractionation related to sublimation processes. Here we can see with the plus and dot markers data from experiments done by Mortimer and Lecuyer, and we see that this experimental data and the theoretical models does not fit. There is no kinetic isotope fractionation model that takes into account the expected physical processes in high vacuum system at very low temperatures. What we did, we built a model considering an open system, and where all the sublimating vapor is being evacuated. So we consider zero humidity, and we consider pure ice with an hexagonal ice structure and a planar specific surface area. So in principle, sublimation is a more complex process, but the determining step for sublimation is the desorption of the water molecules from the surface. So we have used the Hertz-Knudsen-Langenburg equation for sublimation rate, which in reality is an equation for deposition rate. But at low temperatures and low pressure, the interface layer between the vapor and the ice is in equilibrium. So the sublimation rate in the equilibrium cannot be higher than the deposition rate. So it is considered that the maximum sublimation rate is equal to the deposition rate, and this is the equation that all the authors use for the sublimation rate, and is what we use for fitting our model. Because ideally, the isotope fractionation factor need to be calculated with the ratio between the sublimation rate constant, so semi-heavy water and light water, but there is no data for those for the variation of those constants with the temperature down to very low temperatures, and neither about the sublimation enthalpy variation with temperature down to this low temperature. So yeah, we use the same equation that everyone used. And we calculate this isotope fractionation factor with the ratio between the desorption rate constants and the saturation vapor pressure, which return in this formula. At the beginning, we feed the model using, this is the equilibrium fractionation factor, and we feed the model using the equilibrium fractionation factor from the experiments done down to 233 Kelvin. But as you have seen in the previous slide, it doesn't return in coherent data. So what we did to fit the model is use the saturation vapor pressure for light water from Wagner, from experiments done down to 50 kelvins. And then for the semi-heavy water, we have calculated it as the arithmetic mean between the data from Wagner and the data from the International Association of Properties for Water and Steam for heavy water. That it is this model. It can be used down to 150 kelvins, but it works quite well down to 90 kelvins. So another question is whether we expect fractionation in ice. And the answer is yes, because during sublimation, the interface layer is becoming enriched in semi-heavy water. And then the semi-heavy water molecules are diffusing downwards the water ice lattice, down the concentration gradient. And as you can see in this graph here, for temperatures lower than 200 kelvins, the diffusion rate is higher, is faster than the sublimation rate for semi-heavy water. So we consider that the ice is fractionating during sublimation following a Rayleigh-like isotope fractionation, like in the case for liquids. It can be the case that for solids, it can be a bit less pronounced than for liquids, but we use the same principle. So this graph shows our model. In blue is shown the equilibrium fractionation factor, and in violet the kinetic isotope fractionation factor. We can see that it returns in more coherent data. Not that the others that were fit were done only for 233 kelvins, but still differ from the experimental data done from Lecuyer and Mortimer. And so in these graphs show how the initial ice becomes fractionated with the water ice mass loss, depending on the residual ice fraction. If we there are different lines represented depending on the temperature. The solid line is done for 168 kelvins, and the dot line for 198 kelvins, and we see that at lower temperatures we can expect higher isotope fractionation. If we zoom it, we can see that for 30% of water ice mass loss in our model, depending on the temperature, we expect a change in the isotope signature, an enrichment in the isotope signature from 117 to 89 per mil in absolute value for an initial isotope signature of the ice of around minus 76 per mil. And it would represent 155 to 118% of change in the value. If we compare it with the experimental data, we can see that for the data, for Mortimer data, it was only found an 8.7% of enrichment at 198 degrees, and Lecuyer found a depletion in about 40%. Why the experimental data found a lower fractionation than the expected by the theoretical model? One of the reasons can be because the theoretical model is considering zero humidity, is what we can expect on the moon, at the high vacuum that there is on the moon. We can expect that all the sublimated vapor is going to be evacuated to the space. And then we can consider zero humidity. But if the sublimation setup is not, it has not a high evacuation rate enough, then you are not evacuating all the sublimating vapor. So then it can be the case that it's not zero humidity, and depending on the percent of the humidity, the higher percent of humidity, the less pronounced is this fractionation trend. So it can explain on one side why they have found a lower fractionation, and another side, another explanation can be that the Rayleigh fractionation in solid is a bit less pronounced than in liquid. So somehow we may expect something in the middle. Which are, sorry? Which are the implications for the interpretation of lunar water isotope signature? So on one side, we see that the lunar water can be indigenous or later addition water from asteroids, comets, or solar wind, and depending on from where comes from the water, the isotope signature can vary a lot from 13,000 per mil to -100 per mil. The isotope signature from lunar samples range from -380 to +1,400 per mil. That can be due to different origin or to secondary processes happening there. So here in the graphs, we represent the enrichment of the remaining ice fraction depending on the initial, for different initial isotope signature from -800 per mil to +800 per mil. Also from different temperature that we can expect on the moon, from 120 kelvins to 190 to 200 kelvins. What we can see that for light, for very light isotope signature -800 per mil, probably the isotope fractionation is not that relevant, but from isotope signature, for initial isotope signature from -200 per mil to +800 per mil, then if we see at 30% of water ice mass loss, we can expect a relevant isotope fractionation that it can be from 68 to from 38 to 102% of the initial isotope signature. So what I would say that up to 10% of water ice mass lost, we can consider that the isotope fractionation due to sublimation is not relevant. Then the last slide. So the next step is to do this theoretical model for O18 water, and also to extend the model for other ice structures like cubic ice and amorphous ice. Do the model also for icy regolith, considering diffusion, absorption, other parameters, and also to obtain experimental data. This is the prototype that we have built, and we aim to study the sublimation and related hydrogen and oxygen isotope fractionation for pure ice and icy regolith, studying sublimation, desorption, adsorption, isotope fractionation due to these physical processes, to have new data to fit the models. And what is special from this prototype is the high sublimation, high evacuation rate that we aim at having a zero humidity ambient in the chamber, in the sublimation chamber, and a very low gradient within the sublimation volume. So if you are around in Luxembourg, we are going to show it in the LIS Tech Day on 15 June. So come and visit us to in our stand. And so what we aim with all this is to contribute to establish an accurate and robust measurement technique and raw data processing for robotic lunar exploration mission and mission to other planetary bodies. So yeah, I guess I have finished my time. So thank you for your attention, and if there are some questions, happy to take them.